Picture your body 20 years from today. Not your face, not your hair, something underneath, something you never look at in the mirror. Every single day, a quiet mechanical process decides how fast your tissue stiffens and how efficiently fluid moves through it. That process runs through a structure most people never think about, the fascia, the thin fibrous web of collagen wrapping every muscle, organ, and nerve you have. And the part almost nobody explains properly is that one of the strongest levers over that process is something almost embarrassingly simple: whether or not you stretch. And not the way a gym class taught you, the way your tissue is actually built to move. Today we are going down into the physics of this, the collagen chemistry, the cellular signaling, the fluid mechanics. Because once you understand what is happening under your skin, a basic hamstring stretch will never look trivial again. Before we get into the mechanism, if the kind of content that explains the actual biology behind something, instead of just repeating advice, is useful to you, subscribing costs nothing, and it helps this reach the people who are asking the same questions you are. So, let's get into the physics. Start with what fascia actually is, because most people picture it as a vague word for connective tissue and leave it there. Fascia is a continuous three-dimensional matrix built mostly from two proteins, collagen and elastin, arranged in overlapping sheets and cables that surround every muscle fiber, every organ, and every blood vessel in your body. In a young, healthy adult, that collagen network behaves almost like a well-oiled woven fabric. The fibers slide past each other, they glide, they tolerate load and then return to their original shape. Elastin, as the name suggests, gives the tissue spring, the capacity to stretch and recoil without damage. This is why a 20-year-old can touch their toes without warming up much and feel nothing but a mild pull. But collagen is not static. Every strand of it is being broken down and rebuilt constantly through a process called collagen turnover. And here is where aging physics enters the picture directly, as you get older. And this begins earlier than most people assume, sometimes in your late 20s. Sugar molecules circulating in your bloodstream start binding to collagen fibers in a process called glycation, forming what researchers call advanced glycation end products. These are essentially molecular rust, permanent chemical bridges that weld adjacent collagen strands together in places they were never meant to be attached. Once those cross-links form, the fibers lose their ability to slide past each other. The tissue does not just get old. It gets structurally stiffer, less hydrated, and mechanically less forgiving. This is a large part of why a 60-year-old body feels tighter, why range of motion shrinks year after year, and why an old injury that healed decades ago can suddenly start aching again once the surrounding fascia loses its slide. German fascia researcher Robert Schleip, who has spent much of his career at Ulm University studying exactly this tissue, has described a phenomenon he calls fascia hardening, where the ground substance surrounding collagen fibers, a gel-like material rich in hyaluronic acid, gradually loses water content and becomes thicker and more viscous with age and disuse. Fresh, well-hydrated ground substance allows collagen fibers to glide past one another with almost no friction, similar to well-oiled machine parts. Dehydrated, thickened ground substance behaves more like dried glue. The fibers stick together at points where they should be sliding freely. And that stickiness is a large part of what people actually feel as stiffness. Not the muscle itself tightening, but the fascia surrounding it losing its lubrication. Now, here is the physics that most people never get to hear, because this is where stretching stops being a warm-up ritual and becomes something closer to structural engineering. Living tissue responds to mechanical load through a phenomenon called mechanotransduction, which is simply the process by which a physical force gets converted into a chemical signal inside a cell. Fibroblasts, the cells responsible for producing and remodeling collagen, are covered in surface receptors called integrins that physically sense tension in the surrounding matrix. When you apply a sustained stretch, even something as ordinary as holding a calf stretch for 90 seconds, those integrins bend slightly, and that mechanical bending triggers a cascade inside the cell, involving proteins called YAP and TAZ, which travel into the nucleus and switch on genes related to tissue remodeling. Cell biologist Donald Ingber at Harvard has spent decades describing this using a model called tensescrity. The idea that your cells and tissues are held together the same way a geodesic dome is, through a continuous balance of tension and compression, so that a force applied at one point in the structure is transmitted and felt throughout the whole system, not just locally. This means the stretch you feel in your hamstring is not staying in your hamstring. It is sending a mechanical signal through a connected web of tissue that reaches structures you were not even trying to move. Under sustained tension, fibroblasts begin producing fresh, properly aligned collagen rather than the disorganized, cross-linked collagen that accumulates with age and inactivity. In other words, mechanical stretch is one of the few inputs that can directly instruct your cells to lay down younger, more organized tissue architecture instead of stiffer, older architecture. This same principle extends down to an even smaller scale, the behavior of stem cells living inside your connective tissue. Bioengineer Dennis Disher and colleagues at the University of Pennsylvania published a landmark study showing that mesenchymal stem cells, the reserve cells capable of becoming muscle, bone, or nerve tissue depending on their environment, actually choose their fate largely based on the physical stiffness of the matrix surrounding them. Stem cells sitting in a soft, pliable matrix tended to differentiate into soft tissue types like neurons, while stem cells sitting in a stiff, rigid matrix tended to differentiate into bone-forming cells. Your stem cells read the stiffness of your tissue and change their fate accordingly. As your connective tissue stiffens with age through glycation and dehydration, it is not just harder to touch your toes. The physical environment your own stem cells are sitting in is quietly nudging them toward more rigid, less adaptable tissue fates. A mechanical explanation for why aging tissue becomes progressively less capable of soft, flexible repair. Keeping the surrounding matrix supple through consistent mechanical loading is one of the few tools available for keeping that cellular environment closer to a younger, softer profile. There is a researcher whose work explains the cellular side of this better than almost anyone. Helene Langevin, who spent years at Harvard studying connective tissue and now directs the National Center for Complementary and Integrative Health. Her laboratory measured what happens to fibroblasts under sustained mechanical stretch and found something remarkable. The cells physically flatten and relax their internal cytoskeleton within minutes of sustained tension, and this relaxation is associated with reduced local inflammatory signaling. Her animal studies showed that regular stretching reduced the thickness and density of fibrotic connective tissue that had built up around an area, essentially reversing a small amount of the stiffening process rather than merely managing it. This connects directly to a concept gerontologists call inflammaging, the low-grade chronic inflammatory state that accumulates in tissue as we age, driven partly by senescent cells, old cells that stop dividing but refuse to die and instead sit in your tissue leaking inflammatory signals into everything around them. Biologist Judith Campisi, whose research largely defined this field, has described senescent cells as a kind of biological pollution that builds up silently for decades. Sustained mechanical loading through stretching appears to reduce the density of this inflammatory signaling in connective tissue. A mechanical explanation, not a mystical one, for why people who stretch consistently often report less stiffness, less chronic ache, and better mobility years later than people who do not, independent of how much they exercise otherwise. There is also a fluid dynamics piece to this that almost never gets mentioned, and it might be the most underrated part of the whole mechanism. Unlike your circulatory system, your lymphatic system has no central pump, no heart equivalent pushing fluid through it. Lymph, the fluid that clears waste products, dead cells, and inflammatory byproducts out of your tissue, moves almost entirely through mechanical compression, meaning muscle contraction, joint movement, and tissue stretching physically squeeze lymphatic vessels and push fluid forward through one-way valves. When tissue becomes chronically tight and immobile, which happens progressively with age and inactivity, lymphatic flow through that region slows down. Waste products and inflammatory compounds sit longer in the tissue instead of being cleared, which itself contributes to more stiffness and more localized inflammation, a feedback loop that compounds over years. Stretching directly interrupts that loop by mechanically pumping fluid through tissue that would otherwise stagnate. On top of that, sustained stretch increases local blood flow by triggering endothelial cells lining your blood vessels to release nitric oxide, a molecule that relaxes vascular smooth muscle and widens the vessel, improving circulation to the exact tissue being stretched. Better circulation means more oxygen and nutrients reaching cells that are actively remodeling collagen, and more efficient removal of metabolic waste, both essential ingredients for tissue that behaves younger rather than older. Researchers studying vascular aging have also found a related pattern worth mentioning. Comparisons between adults who stretch regularly and sedentary adults of similar age have repeatedly shown measurable differences in arterial stiffness. The same collagen and elastin proteins that make up your fascia also make up the walls of your arteries, and a stiffer, more cross-linked arterial wall is one of the clearest physical markers. Cardiologists used to estimate vascular age, independent of chronological age. The same mechanical principle that keeps fascia pliable through sustained tension appears to apply to the vessel walls themselves, which is part of why regular stretching shows up repeatedly in population studies as a modest but consistent predictor of lower vascular age markers, separate from whatever cardiovascular exercise a person is also doing. Your joints add another layer to this that is worth understanding on its own terms. Synovial fluid. The lubricating fluid inside every major joint capsule is not delivered by blood vessels the way most fluids in your body are. It is produced and redistributed largely through the mechanical action of the joint moving through its range. A process sometimes described as imbibition, where cartilage absorbs fresh fluid during movement, the way a sponge absorbs water when it is squeezed and released. Joints that rarely move through their full range receive less of this redistribution. Cartilage becomes thinner and less resilient over time, and the joint capsule itself, which is really just a specialized extension of the same fascia we have been discussing, becomes shorter and stiffer through the identical collagen cross-linking process. This is a large part of why so much of what people casually call joint aging is really a mechanical disuse pattern rather than an unavoidable biological clock. A hip or shoulder that is regularly taken through a full stretched range tends to retain a noticeably younger feeling capsule than one that has spent years moving through only a narrow protected arc. Your spine follows the same rules, and this is where the physics becomes visible in a way people actually notice in the mirror. The discs between your vertebrae are mostly water-bound inside a collagen and proteoglycan matrix, and like every other piece of connective tissue we have discussed, they rely on movement to stay hydrated. Since discs have almost no direct blood supply, they absorb nutrients largely through a pumping action created by spinal movement, compressing and releasing the disc through its range. A spine that spends most of its day in one narrow seated posture receives very little of that pumping action. Discs gradually lose height and hydration, and the surrounding fascia along the length of the back shortens to match the posture it is held in most often, which is a large part of the mechanical explanation for the height loss and forward stooped posture so many people simply accept as an inevitable feature of getting older. Regularly moving the spine through extension and rotation, the exact motion a sustained spinal stretch provides, keeps that pumping action active and keeps the surrounding fascia from adapting to a permanently shortened, stooped resting length. This is one of the clearest places where the physics of stretching and the visible signs people associate with aging actually overlap directly. The stiffness you feel isn't age. It's a signal that your tissue has stopped being asked to move. If any of this is making you rethink what a simple stretch is actually doing, that is exactly the kind of shift this channel is built around. Taking something ordinary and showing you the real mechanism underneath it. Now, let's be honest about where the popular version of this claim goes wrong, because it does get oversimplified constantly online. Stretching does not reverse your chronological age. It does not rewind your telomeres. And holding a stretch for 30 seconds before a workout is not going to undo decades of glycation overnight. The physics we just walked through describes a slow, cumulative structural process, tissue remodeling that happens over weeks and months of consistent mechanical input, not a single session. Another common misconception is that all stretching produces the same effect. A quick, bouncing ballistic stretch mostly activates a protective reflex called the stretch reflex, which causes the muscle to contract defensively, rather than allowing the sustained tension needed for mechanotransduction to occur. The research on fibroblast remodeling and fascia hydration consistently points to sustained static holds, generally somewhere in the range of 90 seconds to 2 minutes per position, as the stimulus that actually triggers the cellular signaling described earlier. Anything shorter tends to affect only the neuromuscular system temporarily, giving you a brief feeling of looser muscles without meaningfully changing the underlying collagen architecture. This is also part of why stretching once a week produces almost nothing measurable, while stretching most days over a period of months produces changes that people and their physical therapists can actually observe in range of motion and tissue texture. There is one more mechanism worth mentioning here, because it ties everything back to something we have discussed before: the role of chronic stress hormones. Elevated cortisol over long periods has been associated with increased fascial stiffness, partly because cortisol influences fibroblast behavior in ways that favor a more contracted, defensive cellular state rather than the relaxed, elongated state associated with healthy tissue remodeling. This means a body under sustained psychological stress is fighting the aging process on two fronts: elevated inflammatory signaling from senescent cells on one side, and elevated cortisol pushing fibroblasts toward a tighter, more guarded posture on the other. Sustained stretching appears to counter both of these pressures simultaneously, mechanically relaxing fibroblasts while also being associated in several studies with modest reductions in circulating cortisol, likely through its effect on the parasympathetic nervous system when combined with slow, controlled breathing. So here is what an evidence-grounded stretching practice actually looks like. If you want the mechanical benefits rather than just a temporary loosening feeling, target major fascial lines rather than isolated muscles. The back of your legs and spine together, the front of your hips and torso together. Because fascia is continuous and stretching connected chains produces a larger mechanotransduction signal than isolating one joint. Hold each position for at least 90 seconds, breathing slowly, because the viscoelastic creep that allows collagen fibers to actually elongate and reorganize requires sustained time under tension, not a quick pulse. A useful refinement here, borrowed from physical therapy practice, and sometimes called proprioceptive neuromuscular facilitation, involves briefly contracting the muscle you are stretching against light resistance for a few seconds, then releasing into a deeper hold. This temporarily quiets the protective stretch reflex mentioned earlier and allows the tissue to accept a greater range before the sustained hold even begins. Reserve quick, dynamic movement, gentle leg swings or arm circles, for the minutes right before exercise, since that is genuinely a different tool aimed at temporary neuromuscular readiness rather than long-term structural remodeling. And save the long sustained holds for a separate block of time, ideally when your body is already warm, since the two types of stretching are answering two different physical questions, and neither one substitutes for the other. Do this most days rather than occasionally, because fibroblast remodeling responds to consistency the same way muscle growth responds to consistent training. Sporadic effort produces close to nothing measurable. Pair it with adequate hydration, since fascia is largely water-bound to hyaluronic acid, and dehydrated fascia behaves like dry leather rather than supple fabric, gliding poorly regardless of how much you stretch it. Apply gentle heat before longer holds if you can, since warmed collagen has measurably greater elasticity than cold collagen, which is part of why stretching after a hot shower or later in the day when your tissue temperature is naturally higher tends to feel more productive than stretching first thing in a cold room. And move your joints through their complete range at least once daily, rather than only the narrow arc most daily activity requires, since that full range movement is what keeps synovial fluid circulating and cartilage properly nourished over the following decades. The bigger picture here, the one worth sitting with, is that so much of what we call aging is not some mysterious countdown written unavoidably into your cells. A meaningful portion of it is mechanical. It is collagen cross-linking that accumulates because tissue stopped being asked to move through its full range. It is lymphatic stagnation that builds because nothing is pumping fluid through it anymore. It is fibroblasts that stopped receiving the tension signal that tells them to keep producing organized, youthful tissue instead of stiff, cross-linked tissue. None of that requires a drug, a procedure, or a supplement. It requires a mechanical input your body has been designed to receive since long before any of this research existed. And most people simply stopped giving it that input somewhere in their 20s without ever realizing what they were losing. Your fascia is listening for tension every single day. What signal are you sending it? Physical therapists who work with older populations often describe a pattern where the primary limiter of independence in later life is not muscle strength or cardiovascular fitness alone. It is lost range of motion, a hip that no longer extends far enough for a full stride, a shoulder that no longer rotates far enough to reach a shelf, and much of that lost range traces directly back to fascia that was never asked to lengthen for years or decades at a time. What makes this genuinely encouraging rather than discouraging is that connective tissue remains mechanically responsive at essentially every age studied. A 70-year-old fibroblast still bends its integrins and sends the same remodeling signals a 25-year-old fibroblast does when it receives sustained tension. The cellular machinery for this does not expire. It simply stops being asked to run. Your fascia is listening for tension every single day, deciding based on whether it receives that signal, whether to keep laying down younger tissue architecture or to let the older, stiffer version take over by default. So tomorrow, before you reach for your phone, before the day pulls you into everything else it wants from you, give your tissue 90 seconds of sustained tension somewhere. Your hamstrings, your hip flexors, your spine, and understand that you are not just loosening a muscle. You are sending a direct mechanical instruction to the cells responsible for how your whole body is going to feel a decade from now. If this changed how you think about stretching, hit that like button and subscribe for more breakdowns that hand you the actual mechanism instead of a slogan.